pick up on page 44 of the course notes, and we're back to chapter 6.4. And chapter 6.4 goes over sampling distribution, which is a very important topic in statistics. So sampling distribution lets us know how the samples change when you take repeated samples from a population. So generally we'll go out and take one sample and we'll calculate an X bar, or sample mean. But if we went out and took another sample, we'd get a different value for X bar because we're just taking a sample or a chunk of the population. We're not sampling everyone in the population. So we know that X bar is going to be off a little bit. And if we understand how much it's off by, then we can calculate our confidence in our X bar. Okay, so the first definition we're going to go over is the sampling distribution. So the sampling distribution is just like a histogram. It describes the distribution, but it describes the distribution of, say, X bar or some other statistic. So the sampling distribution of a statistic, and sample mean is a statistic, X bar, is the distribution of all values of all, when all possible samples of the same sample size are taken. Okay, so you can kind of imagine a histogram of many X bars, and that's what a sampling distribution is. So go over an example here. A quarterback threw 1 interception in his first game, 2 interceptions in his second game, and 5 interceptions in his third. And we're going to consider this the population. So we only have 3 values for our population. And so when we consider this our population, we use the letter mu for the parameter of the population. Okay, it's not X bar, it's mu. And then we're going to simulate sampling from this population. So mu would really be the average of all these 3 numbers. So mu is going to be equal to 1 plus 2 plus 5 over 3. So 8 divided by 3. That's going to be what mu is equal to. And we're going to simulate sampling from the population. Remember, our population only consists of 3 numbers, 1, 2, and 5. And we're going to simulate taking 2 at a time. So these are all the possible samples with repetition. I can have a 1 and a 1, a 1 and a 2, a 1 and a 5, and then a 2 and a 1, and so forth. So these are all the possible samples, and I'm going to calculate the sample mean for each one. And so I've done it for the first 3. Sample mean for 1 and 1 is just 1. The average of 1 and 2 is just 1.5. The average of 1 and 5 is 3. So I'm just going to do that going down. So 2 and 1, the average would be 1.5. 2 and 2, the average would be 2. 2 and 5, the average would be 7 divided by 2, or 3.5. 5 and 1, the average would be 6 divided by 2, or 3. Here I get 3.5, and here I get 5. That's a 3. Okay, so here's my sampling distribution. I only have, looks like 10 possible values. Remember, this is just a small example to demonstrate what a sampling distribution is. But I might want to plot those values. So I'm going to make a dot plot with these 10 values. Okay, so I had the number 1 appear once. 1.5 appeared once. So again, I'm just creating a dot plot with these values. 1 appeared once, 1.5 appeared once. I'm just going to continue in that fashion. So 2 appeared once, 3 appeared twice, 3.5 appeared twice, 4, and then the last number was 5. Okay, so here's our sampling distribution. It's the distribution of all possible samples when the sample size is 2. So one thing we might want to know is the center our sampling distribution. And so we can take the average. Now we're taking the average of all the x bars. And so when I do that, I have a 1 plus 2 plus, oops, I skipped 1.5 plus 2 times 3 plus 2 times 3.5 plus 5, and that's all divided by, let's see, how many do we have? 1, 2, 3, 4, 5, 6, 7. Actually, there's only 8 here. Oops. Okay, and we actually get, or let me count, I think I missed one. There's 9, so what did I miss here? 1, 2, 3, 4, 5, 6, 7, 8. I got a 1. I missed something. I got a 1, a 1.5. Oh, there's two 1.5s. Oops. There should be another dot there. So I want to add another 1.5. And then I want to divide by 9. Okay. So, and this works out to be the same thing as our population mean, 8.3. Okay, so when we took random samples of 2, on average we got something equal to our population mean, which we calculated as 8 over 3, if you remember, up there. Okay, so what this shows is that x bar is an unbiased estimate of mu. On average, x bar was equal to mu. And so that means that x bar, though sometimes it's higher, sometimes it's lower, it doesn't systematically under or overestimate mu. So we say it's an unbiased estimate. Okay, and what we just saw was an example of sampling variability. That means the samples vary from sample to sample. We're not surveying everyone in the population, so our samples are going to sometimes be off by a little bit. Okay, so let's write down the definition of that. So sampling variability implies that statistics, like the sample mean, will vary from sample to sample. It just means that if your neighbor went out and took a sample of students' GPAs and you took the same sample but a different random sample, you'd have two different numbers, although they'd probably be fairly close to each other. Okay, so let's finish this off by doing the examples on page 46. So what does it mean when we say that the sample means target the population mean, or the sample mean is unbiased? Okay, all that really means is what I just underlined here. X bar does not systematically under or overestimate the population mean. So the statistic does not systematically under or overestimate the population mean. Okay, so the next question says, based on a random sample of 40 voters, the NBC News division predicts that the Democratic candidate for the presidency will get 49% of the vote, but she actually gets 51%. should we conclude that the survey was done incorrectly? Okay, so this is an interesting question because this happens quite a bit, and that's why when you look at political polls, they always give you what's called a margin of error. Because we're taking a sample, we expect the statistic to be off by a little bit. It doesn't mean that we did anything wrong, but we always should report how much we think we're going to be off, which is called the margin of error. So she would be incorrect in not reporting that, but it doesn't necessarily mean she did anything wrong. Okay, and the last one, we have a sample of body temperatures. If we were to construct a histogram to depict the shape of the distribution of that sample, would that histogram show the shape of the sampling distribution? And so if we just make a histogram of the data, the histogram showing the distribution of the individual values. Not the sampling distribution. So there's a difference between showing the sampling distribution, which is the distribution of x bars, versus just the distribution of the individual values you get in your sample.